Okay, the section that we focus on in this video is the elementary row operations and what they are used for in matrix algebra. We will learn about the following important ideas: Gaussian reduction, Gauss-Jordan reduction, as well as Cramer's rule for solving systems of equations. Let's see how this works. First of all, the elementary operations. There are three kinds of elementary operations that we will perform on a matrix. Okay, now remember, just to remind you, the matrix has rows and it has columns. We're going to focus on the rows. Okay, so we interchange two rows or columns. That is one operation that we can perform on a matrix. So you'll see the matrix is row 1, 3, minus 2, 4. If I interchange the two rows, the minus 2, 4 becomes the first row, the 1, 3 becomes the second row. Okay, and if I interchange columns for that matrix, it means that the column that has a 1 and a 2 in it, and the one with a 3 and a 4 swap around. Okay, so we'll see the 4 over 3 becoming column 1, and minus 2 and 1 becoming column 2. So we can swap rows and columns as we need. That's the one operation. The second operation is we could multiply each element in a particular row by a non-zero number. It doesn't make sense to multiply it with 0 because then the row disappears. So if I have here, for instance, now please guys note the notation that we're going to use. That little prime indicates the new row 2 is minus a half times the old row 2. So I'm multiplying the new row 2 for the old row 2 with minus a half to find the new row 2. Then we'll see, if we take minus 1 times minus a half, the result is 1. If we take 4 times minus a half, the result is minus 2. The third operation is we're going to multiply a row or a column by a non-zero number and add this result to another row. So we can interchange, we can multiply with a scalar, and then once we've multiplied with a scalar, we can now add it to another row. Okay, so this is what we did over here. We formed this matrix by saying the new row 2 is minus a half times the old row 2. And then we're going to say the new row 2 is the old row 1, which is this row 1, minus the old row 2. So the new row 1 will be the old row 1 minus the row 2. So 1 minus 1 is 0. 3 minus minus 2 becomes 3 plus 2, which is 5. And this is the result of that, what we call a row operation. Okay, so let's see. For 3 by 3 matrices, we've got a 3 by 3 matrix over there. If we want to find a new row 2, we can say the new row 2 is a half of the old row 2. Now what will happen then is that this number will become a 1 and that number will become a 4. Now we're going to see later on that that is going to be a necessary operation in the work to come. If we want to make this row, this one here, a 0, for instance, the new row 3 will be the old row 3 added to the row 2. So if I add those two, I get a 0. Now let's see. Row 1 is unchanged because I didn't plan to do anything with it. Row 2 was the old row halved. So that was half to become 1, that was half to become 4, that remained 0. Row 3 was the sum of the old row 2 and the old row 3. So minus 2 plus 2 is 0, 8 plus 3 is 11, 0 plus 1 remains 1. Okay, so let us see. Now we've got our matrix looking like that with these row operations. Okay, so if I want to now form a new row 2, I can take row 1 and subtract row 2 from it. Now the purpose of that would be to create a 0 in that block. If I subtract those two, I create a 0 there. Now you're going to see in the work that we're going to work with today, we want to create ones and zeros in our matrices. Okay, so once we've done that, we can see that minus that is 0, minus 2 minus 4 is indeed minus 6, 4 minus 0 remains 4. Of course, row 3 remains untouched. We did nothing to row 3. Okay, so I think we're ready to start our focus on Gaussian reduction. Now with Gaussian reduction, we want to solve systems of equations using matrices. So suppose we want to find a solution to two algebraic equations. x1 plus 3x2 is 5 and x1 minus 2x2 is minus 5. Okay, so what do? A system of linear equations we will represent in a matrix using what we refer to as a coefficient matrix and a constant matrix. So if I have to form my coefficient matrix, I'm looking at what is in front of the x's. Okay, so my coefficient matrix, I align these two and then I form a matrix from their coefficients. So 1 and 3, there we go, entry 1, entry 3. 1 and minus 2, entry 1, entry minus 2. That takes care of the coefficient matrix over there. The column matrix that follows will then be the constants. So the coefficient matrix is a 2 by 2 matrix since there are two variables in this equation. So let's look at the constant matrix. Is a column matrix with those two entries in it, 5 and minus 5. Okay, so the constant matrix is a 2 by 1, important, 2 by 2, 2 by 1 matrix, column matrix. Okay, so let's see how will we go about solving the system of equations using Gaussian reduction. Okay, so to solve this, we will form an augmented matrix, folks. Now we know what that is. We've heard about it in the past. What will we augment this matrix with? We're going to augment it with the constant matrix. Okay, so we append the two. The augmented matrix is obtained by appending the columns of the two given matrices, usually for the purpose of performing what we're going to see, row operations on each of them. So let's see, the augmented matrix is the constant or the coefficient matrix augmented with my constant matrix. And I'm ready to begin. There's my my coefficient matrix, there's my constant matrix. I have formed an augmented matrix by using those two. So now I'm going to work with this system over here, the new matrix, the augmented matrix. Okay, I want that one that I've just circled and colored for you to be a 0. Remember I said at the beginning, we want to change ones to zeros and other numbers to 1 so that we can find our solution. So to get that as a 0, it makes sense to subtract the two rows from one another. Okay, so we want the 0 in that position. So the new row 2 is going to be row 1 minus row 2. Now if I do that, I get 1 minus 1, which is 0. I get 3 minus minus 2 is 3 plus 2, which is 5. And I get 5 minus minus 5, which is 5 plus 5. That gives us a 10. Now what's interesting here is you can see that we have a multiple of 5 in each of those numbers. We can change that by dividing this whole third row by 5. So that 5, in fact, we now want to be a 1. Okay? And the easiest way to do it is to take the old row and to divide that old row 2 with a 5. If we do that, we get a 1 in that position. You can see there's my coefficient matrix. Now can you see, folks, that on the diagonal of the coefficient matrix we have 1s. So we have completed our job. We can now deduce that from that pair of numbers together, that x2 is indeed 2. Why? Because this is 1 times x2, which is equal to 2. From the first row, we now have that x1 plus 3 times x2 is 5. We have just found x2, so we can substitute it into the equation for x1, and that gives us x1 plus 6, which is equal to 5. The 6 transposes to the other side, and we have x1 as the number minus 1. So there's my solutions to this system. What did I do? I did Gaussian reduction to solve the system of equations. Now remember, Gaussian reduction, you want to form an upper triangular matrix in your coefficient matrix. So you want everything here below that 1 to become 0, and to the left of this one to become 0, and everything on the diagonal you want as 1s. How do we do it? Well, we operate on our rows by one of the 3 elementary operations we've seen so far. Okay, so we begin by considering a system of 2 linear equations with 2 variables. You are given 2 lines, folks. These are lines. If you draw them, it's equivalent to x plus 3y is 5 and x minus 2y being 5. Okay, so they give us 2 lines. One and only one of the following type of solutions could occur. You can have a unique solution, folks, if the lines cross in one point. Okay, then the solution is unique because there's one intersection point. Secondly, you can have 2 lines that are parallel and coincident. It means they have the same gradient, and as you can see, they lie on top of each other. So systems like that has infinitely many solutions. Then your third case, the 2 lines are parallel, but they are distinct, so they do not lie on top of each other. They lie alongside each other. There's no solution there, because those lines will never intersect. Okay, how does this work then if we have a system with 3 variables in it, x, y, and z? Well, there's such a system, x, y, and z. We have the representation of this system in planes because it's in the 3rd dimension. So if the 3 planes intersect in one point, you have a unique solution. Now there's ways to check if this is going to be the case or not. If the 3 planes intersect in a line, you can see over there, there's infinitely many solutions. Then if the planes are parallel to each other, clearly there's no solution. So the notion of a line in 2 dimensions gets replaced with a plane in 3 dimensions. Okay, so there's a system of equations that we are looking to solve. We want to solve that system. So first of all, we prepare an augmented matrix to start our row reduction. Now remember, your augmented matrix has the coefficient matrix and it's augmented with the constants. Okay, so there's my augmented matrix. Okay, let's start the process and let's see how it works. This is exciting, but follow carefully because you can make silly little errors if you do Gaussian reduction. Okay, let's see. First of all, there's quite a few things we can do here. We can interchange those 2 rows to make that a 1. The ultimate thing for us is to have a 1 here, a 1 there, and a 1 here, and all of these turn into zeros. So we can interchange those two rows, or we can say the new row 1 is the old row 1 minus row 2 will give us a 1 in that position. There's pretty much a lot of things you can do. So some of you might start it differently, but you will get to the same answer. Okay, what did I do here? I said I'm going to take a new row 2 is formed by taking row 1, that row up there, and minusing twice row 2 from it. And then for a new row 3, I'm going to take row 1 and simply just subtract row 3. Now that will have it will have an advantage that this number here is going to become a 0. The advantage of doing this to the row 2 is that we create a 0 over there. So for now I decided to leave the 2 at the top. If we do that, we'll see we get to this particular answer. Now folks, do this on a piece of paper. When you do your row operations, have a piece of paper on the side, write them out and do the operations so that you see what you are actually doing. Okay, so now we can choose. Let me hide that first. We can now choose to do two separate things here. I want to have this there as a 1. So I can divide by minus 5. Here I want a positive 1, so all I'm going to do is multiply with a negative 1. Now let's see if that is what I did. No, I first of all, for the third row, yes. For this row, I first changed the sign, which I could have done immediately. I could have divided or multiplied by minus a fifth. But having done that, I changed the sign of the third row. That row is perfect. Okay, there's a 0, here's a 0, and there's a 0. Now I've changed the sign of the second row by saying that the new row 2 is the old row 2 multiplied by minus 1. Now, to get this into a 1, I can simply divide everything by 5. Okay, but let's see. Is it necessary to do? Yes, we'll talk about that in a moment. I've got my first solution there. My first solution says that z is equal to 60 from the bottom line. So I've reached a point where I can do what we call back substitution in the Gaussian reduction. I back substitute it and then I solve the variables. The second line represents 5y plus 3z is 420. I know that z is 60, so I substitute it in and I get to y, which is 48. Now I've got z and y. I go to my first line, I plug them in, I see that 2x is 72, so x is equal to 36. So there's quite a few things that happened here in the work that I was looking at. First of all, the whole purpose of Gaussian reduction, folks, is to form these zeros over there. Let me get the pen. Is to form the zeros that I want over there. Once I've got the zeros, I can start back solving, because this is just z that's equal to whatever the constant is. So in this example, I did not change the 5 to a 1, and nor did I change the 2 to a 1. For now, because I'm only working with Gaussian reduction. Okay, so I can do it that way, but what I'm going to encourage you to do is to get this diagonal there to have 1s on it. And you'll see why that's important, because that leads us beautifully into our second method. Okay, let's look at solving this set of variables using a Gaussian reduction. Okay, folks, there we go. I would ask you to pause your video at this point to try and apply what I've just done, and then come back and unpause and see where you went wrong or what you could have done differently. Okay, let's have a look. We prepare the augmented matrix and start with our row reduction. There's our augmented matrix. Now remember again, Your augmented matrix has the coefficient matrix augmented with the constant matrix, the column matrix or column vector, which contains those constants. Yeah, folks, we're augmenting it. We're not throwing these over the equal sign, because then the signs would have changed. We're just augmenting the coefficient matrix. Okay, so there we go. Now we've got a few choices. We can change this to a 1 and interchange those rows, or we can simply say for a new row 1, we're going to add that row and this row together, which will give us a 1 there. There's quite a few things we can do. Or I can just divide everything by 2, because everything in row 1 is a multiple of 2. To get a 0 here, I can say row 2 plus 3 times row 3, because that will change this into a 3, and 3 minus 3 is indeed 0. So let's see what I suggested. Yes, I suggested that we make the first row halve everything, and there I have the 1 in the position that I wanted. So I'm not going to touch this row again. Row 1 is taken care of. Now we can see, to find a new row 2, I have now 2 options here. I can multiply this with 3 and add them, or I can multiply that with minus 3 and add it for a new row 2. For a new row 3, it will make sense just to add row 1 and row 2, because that will create a 0 over here. So let's see what I suggested. I said let's interchange row 3 and row 2. Okay, that's fine. That just means this goes over there, and then we can continue with our operations. Okay, so let's see, did I now suggest a multiplication of 3, or did I suggest an addition here? There's 2 ways to get this to be a naught. We can add those 2 together, or we can multiply this with a 3 and add them together for a new row 2. Remember, we are not touching row 1. So the positions that we're looking at is making this into 3 zeros. Let's have a look. If I take row 2, the new row 2 will be indeed then row 1 plus row 2. That will give me a naught there, a 3, a 5, and a 13. The new row 3, I said, let's multiply row 1 by 3 and subtract it from the old row 3. So that will become 3 minus 3, which gives us a naught over there. Okay, have we done that? We will get to this matrix over here. So far that's untouchable. This is exactly what we want it to be. The only thing that may become a naught now is that minus 2. Okay, and hopefully this will become a 1, and that will become a 1 in our process. Now it's quite nice to see over here. Everything is a multiple of 2. So I can also divide by 2 there. I'll divide by minus 2 and get this into a positive 1 if I want to. Let's see what I suggested. I suggested just halving every entry and turning it into a 1. Okay, so there we are. I'm very safe. That I don't want to touch, that I don't want to touch, I don't want to touch this. Now this must become a 1 and this must become a 0. Or I can get this to be a 0 quicker and try and get this to be a 1. There's quite a few things that I can focus on now. So what I would have suggested now for myself is for a new row 2, there I do not want to lose that position there. I want that to be a 1. If I am going to lose it, then I multiply this with 3 and I add the 2. Then I have the 2 zeros in place in the top row. Let's see what I did. Okay, now I said the new row 3 will be row 2 plus 3 times row 3, like I suggested over there. Okay, if I do that, then I do get my 2 zeros. And that's 0, and I don't want to touch this. Okay, and you can see, folks, the only thing that's left for me here is to start back solving. Now I want to back solve as quick as possible so I can get the job done. Okay, so let's see. I now have a choice of either dividing this whole thing by 2, which will leave a 1 and a 2, and then leave that there and back solve. I don't know what I did, so let's see what I did. Oh, I changed both. In fact, I went and I also said in this example, I want to get this 3 to be a 1. Okay, how do I get it to be a 1? Well, and the new row 2 will be the old row 2 times by a third. Okay, once I've done that, I get a 1 in that position. Once I perform this operation, I get a 1 in this position. And then I have a diagonal of 1s available. And look at this, folks, I'm ready. I've got that, this, and this. I have the 1s on my diagonal. I have the 1s available on my diagonal, so I can start solving my equations and back solve. First of all, z is 2. That I see from the last line. Okay, now y plus 5 over 3z will be 13 over 3. But now remember, I've got z. Z is 2. Now here I don't like working with fractions, so I always play it safe. You can make the most silliest mistakes with fractions. So just multiply everything with a 3 to get rid of the denominator. Then you have 10 equal to 13, and you get your answer there, which says that y is indeed equal to 1. Okay, so with that, I can now solve my third line over there. X plus twice y, which is 1, plus 3z, which is 2, is now 11. If I solve it, I get that x is equal to 3. I hope you got that answer. If you didn't get that answer, folks, I try as much as I can to discuss all the options we have and then go for one of the options to solve and see where we go. You might have done it in less steps than what I did. Nothing wrong with that. As long as your answer at the end of the day is x is 3, y is 1, and z is 2.